So I am recording. And so good afternoon, people. Be welcome to this new session of our MathBio seminar. And today we have our second international speaker. Her name is Olga Sobetska, and she's working closely with Professor Tomás Veloz, who is a colleague here from the Department of Mathematics of UTEM. Just to know a little bit more about Olga, I have here some kind of short biography. Olga has a bachelor degree and she is currently completing her master's degree in sociology at the University of Leipzig in Germany. She has been specializing in quantitative sociology and data sciences. Her academic interest has been a deep understanding of research methods. She has extended this interest to topics from other disciplines and has developed a fascination with quantum physics and medicine. Still, as a sociologist, she remains interested in some social and cognitive subjects and phenomena, such as the balances theory, dual process theory, and the phenomenon of the conjunction fallacy. She focused her research on combining the social sciences with the natural sciences, especially with the methods of computer science and chaos theory, to explore new connections between these disciplines and their approaches. Okay. Olga is going to give a talk entitled Relevance of Null Hypothesis Significance Testing in Biomedical Sciences, a sociological approach. So Olga, please, you can share your screen right now with your presentation. Okay.
Okay.
We are going to have at the end of the talk 20 minutes to make questions. But if there is anyone who wants to interrupt their talk and the exposition and make a question, just do it, okay? So Olga, be welcome. Yes. You can begin.
Yes, you can see my screen very well.
Yes, yes.
Okay, perfect. Thank you very much for short presentations. I'm also very happy to participate as for me international seminar and being your international speaker. I right now indeed currently finishing my master degree.
Hello, can anyone hear Olga? Do you hear Olga?
Very excited to present you my paper, which was submitted in May, I think. And if you need details, you can ask Francisco after or me. I will send you the full link. So I would like to begin. So the title of the article which was published is Relevance of Null Hypothesis Significant Testing in Biomedical Science. And this paper is also focused on the sociological approach to highlight this problem. So this is the points which we will discuss during the session. First, I will present highlights of the article, the most important points, what is the article about. For those people who read it, it would be great to repeat one more time. For those who didn't read, you will get the insight of the main and motivation of the paper. Then, because I didn't know who knows already, who worked with the null hypothesis significant test, or in following, I will just call it p-value test, which is the same. Anyway, to bring our together on the same page, I will give a definition of this test, practical example in biomedicine, so you will understand real relevance of this test in biomedicine. And then we will discuss the correct interpretation and, unfortunately, the misinterpretation which we meet in science today. Then I will discuss the state of this test in academia, how popular it is, how correctly it's used, the interpretation from other disciplines, giving you insight with the empirical studies, which focus also on geographical and multidisciplinary aspects of this problem. And in the end, I will propose the format of future survey, which could give us in theory a bit more structure on this problem. And after this, we will start our discussion where you can ask me main questions and so on. So the significance test is one of the most popular tests in academia, and in bioscience, it's a gold standard for many research and stuff. And that's why this plays really a crucial role in the whole academia and research. Unfortunately, by the mathematical purpose, it's not interpreted correctly always. And the degree of this interpretation is enormous right now. The misunderstanding and erroneous conclusion based on this method lead to distrust in the statistical method. And right now, if you will Google or you will check the literature about this test, most of the article will contain word misunderstood, misinterpretation, and so on. So because right now, this test became really negative more than positive. So in my article, I highlighted the importance of this test in biomedical field as well, as this huge field of research. And to understand this problem better on some cognitive level or some theoretical level, I proposed the theoretical explanation which I took from the sociology. So in the end, this paper propagates correct interpretation. So in the end of the seminar, you will understand how it should be interpreted if you whenever decide to use this test. Also, I will explain the alternatives because this is not the only one test which can be used in research. And then you will also see how this test is used based on disciplines and locations in which countries and so on. And also we will determine the extent of misspecification at the academic level, which I think for us could be the focus of discussion. And as a result, after the meeting, you should get the practical and theoretical arguments which address the problem with null significance hypothesis testing at the multiple levels. So I begin with a definition. So very briefly, because it can take hours to discussing the formulas, to discussing the constants and so on. So because we have here people from different fields, I will talk about this test more general. So this is a null hypothesis significant test or p-value test. This is a statistical method which is used in inference statistics. In the mathematically speaking, it gives you probabilistic statement. So it applies some formulas, it applies some constants, and in the end, you have the probabilistic statement which researchers interpreted in the focus of their theoretical question. It's used everywhere where data is provided and where research question is formulated. So basically, it has no limits. So this probabilistic statement, this is it used to establish the probability that the difference between the two populations, for example, before treatment and after treatment, or pre-stimulus or post-stimulus, is not random with a certain level of confidence. So basically, it's like, okay, we have the mean of blood pressure before treatment and after. So how random is this difference? So this is the question which p-value is trying to answer. So to be more formal, because we still have mathematicians here, we will talk about such parameters as null hypothesis, or it's the null hypothesis means, so this is hypothesis which tells you that between your parameters in your theoretical question, there are no difference or zero effect. That's why it's null hypothesis. The alternative hypothesis tells you that we, in theory, may have some difference. And this alternative hypothesis can be one-tailed or two-tailed. What does it mean? It means that we just can say that these two observations are not equal, or we can say that one observation is more or less than another one. That's why it's one and two-tailed. So alpha, you will see it after. Alpha is the significance level. This is the theoretical threshold value from which we understand that our difference, our observed difference is random. So we take it theoretically, but in last decades, or I don't know, last 50, 60 years, many, like most of researchers, use 95% as alpha. So, and p-value is the endpoint, the end calculation. This is exactly what we need here. So this is the conditional probability of achievement of observed outcome. So this calculation, this procedure, like all other, has some assumptions. So first is the population is normally disturbed, or the sufficient large sample, said by central limit theorem. So what central limit theorem says is that we need to have at least n more than 30, so more than 30 participants in an experiment. But to really establish the effect, you need more than 100. So it's very shortly. And the last and the most important assumption is that null hypothesis is true. So we go through all procedure, we use all this parameter, we calculate everything, assuming that our null hypothesis is true, so that we have zero effect. And based on this, we calculate, we make procedure, and we get results and interpret them. So in biomedicine, you can see that it has, just a second, I'm sorry. So can you see my screen?
Yes, we can see.
Okay.
Perfect. Yes.
Okay, great. Sorry. So, and the biomedicine, you can see the application of this test in the following question. So basically, my biggest motivation to learning this test so deeply came from medicine. So this is about drug treatment, this is about medical experiments and so on. In medicine, this is a gold standard, and you can see it in almost all research and studies. Before P-war, I would say, it's the time when people finally understood that there is a big misinterpretation and started to limit or forbidden this test, and also today. So For example, if we want to examine if a new drug treatment significantly reduce blood pressure in patients with hypertension. So what we do, we set the null hypothesis and we say there is no significance difference in blood pressure between groups pre-stimuli and after stimuli. So the drug doesn't work. Or we say we set alternative hypothesis that there is a significant difference, or we can also give the direction, bigger or larger difference. So it depends on the research question. Second example is that I think it's more in biology. Does a particular pesticide have a significant impact on the survival rate of a certain species of insects? So here is the state. We set null hypothesis and we say there is no significance. In alternative, we put yes, we may observe the significance difference, and also always we can set the direction depending on the idea of research and based on the format of research question. So these two examples are widely used in biomedicine. I mean, when I did research, I met these ones or some similar, and I hope this will clarify you how the test is connected with biomedical field. So we set up the hypothesis, null hypothesis and alternative. What's next? So we collect data. Basically, we check assumption that we have enough of participants in group, that it suits the central limit theory and stuff. Then we calculate the p-value considering the nature of the data, because p-value test, it's a group of tests, and for each kind of distribution, for each kind of data, we need to use different mathematical approaches. It can be t-distribution, can be chi-square distribution. It also can be if it's probability, meaning when we say not difference, but if it's zero success, or sorry, zero failed, one success, then it will be another, it will be binomial distribution, and it will be a bit another procedure in formulas. But in the end, it always gives us p-value, and this is the value we interpret in our research. So we got it, and we set up the significance level, for example, 95%. Sorry, so it's 5%. So if we got the p-value less than 5%, I would explain 5% one more time. So it was here in, sorry, it was here, the significance level. This is a theoretical threshold or limit point. And now I'll explain what does it mean. So this is exactly the point where we say, okay, after this limit, the probability will be that high that this difference exists, that we keep the null hypothesis. So, and it is like this. But if we say that the probability is smaller than this 5%, then it means that it's really too unlikely that this difference is random. So, and you also can put 1% and significance level 99%. You also can put 90% or 85%. I think this is the most used, but kind of standard is always 95%. So this you will see in most research. So this is about the interpretation. So when you calculated the p-value, you know which hypothesis you need to remain and which to reject. And this process is the most important. And this is actually the source of misunderstanding and of mistrust. So because rejected and maintained. So what does it mean? Null hypothesis is rejected. It means that we say that there is not zero effect, that there is an effect, right? So the drug works. And what happened in medicine, you take this conclusion and you say, yes, okay, drug works, so we, for example, send it to the market. But actually, it's not completely correctly, because first of all, especially in medicine, statistical significance, it's not necessarily clinical significance. So if you found the effect in some therapeutics, you need to make sure that you repeated this this experiment, this drug, and you applied other statistical methods. And also, if you didn't get any result, it doesn't mean that your drug doesn't work, because the clinical significance of medical significance can be huge. The thing that you didn't find an effect with these drugs can explain more effects of other drugs, or like their connections and so on. That's why in medicine, this is incredibly important to not to switch these two definitions. So, and by purpose, this test was created by Fisher, a prominent mathematician. So, and in his classical explanation, he always said that it should be used like for filter hypothesis to see how flexible you are with your data, how flexible you are with your hypothesis, and so on. This test was not made to really establish the effect. And this is what exactly happening right now with drugs, with some, how to say, for example, in social science, it's made for some social parameters when scientists say that one parameter is more important than another, but actually they both can have no importance, and so on. So if you also keep in mind that null hypothesis testing is not for establishing the effect, but for filter the hypothesis, you know that for correct scientific conclusion, you need to use other tests as well. You also know that if it's about medicine, you need to mind the clinical significance of these tests. And of course, if you made all calculations correctly, then you can say that, yes, exactly. So p-value below a predefined alpha level means that the observed data is unlikely to have occurred if the null hypothesis were true. In other words, it indicates that there is an evidence against the null hypothesis and provides support for the alternative hypothesis. So it means that the hypothesis and the data, which gives you a significance result, motivates you to compare it, first of all, with other hypotheses and with other data. Second of all, to motivate you to check it with by another test. So what went wrong is that p-value, as I said, it's not an indication of the strength or magnitude of the effect. P-value is not the probability of the null hypothesis of being true, so this 95%. As I said, and it's very, very important point, that clinical significance and statistical significance are not the same. Based on these points, p-value interpretation is also performed ignoring critical thinking, because here in this interpretation, I was presenting the idea that you need to keep in mind this, you need to keep in mind this, you need to know how to do this. You always need to keep focused on your research question. And this is what not always happening in research. And by critical thinking here, I mean that if you see the probability value, it's not always a probability which you found a result. So you need to go deeper in the definition of this probability and give the conclusion based on this definition. So Also, one of the biggest problem is that mathematical problem, I would say, of this test is that by the nature of the calculation, this test is sensitive to sample size, because the formula is the following. You take the mean, for example, if we take of blood pressure, then we take the mean of blood pressure of participant before treatment minus after treatment, and we divide it in the root from standard deviation divided by n, so the number of participants. So by this formula, we can see that the bigger n, the more likely we will get significance results just by its mathematical nature. And that's why most of big samples, so 1,000, 2,000, 10,000, will probably lead you independently from the truth to a significance result. And this is also a part of critical thinking, which I mentioned. Also, this we speak a lot about if the results was found, but what we do if result not found. If you didn't find any confirmation of your hypothesis, it doesn't mean, based on this test, that your hypothesis is wrong. So exactly, so this is non-falsification of a hypothesis. It's not the same as confirmation of a hypothesis. It's like if you didn't find any effect, you actually can't confirm the null hypothesis is true. It means that you need to try other tests, you need to try to check your data, to check assumptions, and so on. But the case which motivated me when I was learning this test at the university, it came from a medical study from a cardiologist. He was presenting, it was some prominent American cardiologist, and he was presenting his study about his new drug to the audience. And in the end, he showed 5.6 or 7% of this p-value. So, and then the people, they didn't believe him, and they say that the study is failed. So, and here we can see that there are many things went wrong here. First of all, it's not clinical significance. Second of all, it's not a confirmation of zero effect, and so on. So we can see that these points are, in most cases, just ignored. So yeah, this everything, unfortunately, not just rare cases or specific cases. I would say this is scientific routine. This is what always happens, like every day. And so many scientists already started the p-war. They fight to limit or to prohibit this test at all. And American Psychological Academia, they said that they don't accept studies only they don't accept studies with only p-value. They request other tests and other conclusions for further publication. So it was first win after many years of p-war, and it's still going, it's still ongoing. We spoke a lot about study level, about research level, but actually there is also a big problem at the universities, in schools, who still learn the p-value concept and during their study, and they also learn it not correctly. And we will, I will show you further some evidence, some empirical evidence for this. So the other more valid tests are less popular in academia and in universities because they're also complex, but they really valid by their mathematical nature. So I mean here confidence intervals, effect sizes, machine learning, which pop up recently, and Bayesian inference approach. And these should be considered just a tool for learning and understanding this test. So yeah, this is results of researchers, sorry. It's many years, so since 86. These tests were made to understand the level of understanding and correct interpretation of p-value tests by academical psychologists. Or there also was like methodological instructors and so on. And we can see that basically it's not many things changed. And here you can see, I will explain in details. So here you can see the recent study, well, recent 2015, but still recent. This is results of this test to establish the level of understanding of p-value concept by academical professors. Their mean number of the years working in the university is 14 years. So they are senior professors. Here you can see the vignette of questions. I must say that all of them are false from start. And in the end, you can see how many participants, how many academical professors rate the all 5 statements as false, basically, which is correct. So you can see that by first group, which were personality evaluation and psychological treatment, it's only 4% who understand the concept. Then in behavioral science methodology, which is directly connected to this test because it's methodology, only 20%. And then it's psychology, social psychology, psychobiology, which is 0. And development and educational psychology, which is 6. And these professors, they work with p-value ongoing, and they teach these tests to students. So, and this is how they really understand their concept of p-value. And what's going on after, they teach it correctly, missing some points, probably. Students take this information, finish universities, go further in research in academia, and then we have misunderstanding in research. So this is the circle which I suggest, like I see, based on this empirical evidence. So by students, I must say that it's not always depends on psychology or like social science. Students from many areas don't understand this concept entirely. And this study, for example, this is from China. So this was from Spain, and this is from China. So we can see that, first of all, the misunderstanding of this concept is not really depend on the degree, if it's bachelor, if it's master, PhD, and so on. And also, it's not really fully connected to the discipline. So, of course, you can see on the B graph that participants from math and statistics have the lowest rate of misinterpretation, but it's still very high for people who learn statistics deeply. So, and here, this graph, this study is very interesting because they also rate the level of understanding of CI is confidence intervals, and this is the most popular alternatives to significance tests. And you can see that it's also not optimistic image, I would say. So further, it was a big study from Chinese researchers. You can see that in many fields they make mistakes, and I mean, like, to which exactly mistakes. So you can see here the vignette of questions which are asked, which are really proof if you really understand the concept, if you really go in easy thinking and you apply this 95% as the probability of a null hypothesis being true, of finding the effect, or so on. And here they have a vignette also of questions with non-significant scenario. So here they ask, here the vignette was like, considering you make the test and you got the p-value is significant, and then they ask these questions, and these are the results for this test. And then they did the same, but they changed the number and they said like non-significant, and it didn't went really better. So yeah, in the last study, there is this is very recent. Yes, in 2022, which were tested in Sweden, and this is really interesting statistics about the study, because you can see that, for example, people who don't work professionally with statistics, it's like only 6.8% who correct answer to how to say, to test to understand the level of understanding the concept of null hypothesis and alternative hypothesis. And people who work professionally with statistics, it's only 15. So it's not, I would say it's not even more than 50%. Also at the research level, you can see that there is no difference if it's less or more than 5 publications. The PhD degree also doesn't play significant role in understanding root of this problem. And surprisingly, we can see that women understand better this concept than men. So I'm a bit out of time. So I will present the sociological approach very, very shortly. I'm sorry for being out of time. So we saw evidence that this is a hard topic, and this is not depends on PhD, on publications, on degrees and stuff. So there can be some other theoretical reasons. And I use source theory to explain this problem, which is actually means that when you are in a student and professor relationship, you kind of produce the huge authority degree to this professor, and your professor became the source of the information you get. And because of the effect of authority, you are less, how to say, less motivated to check this information to which your professor gives to you. Because when we take information for professors, we know this person is much older, much smarter, has more degrees than me, and he has much more authority than me. Then of course I need to believe him. And this is how our daily communication is built. But imagine if the professors provide the wrong interpretation of this test, there are less probability that the students really will check this information. So they take it and they go with this information further in their scientific career. So I took this theoretical idea and built the hypothesis that given that the level of competence of an instructor in p-value test is low, which we saw before in empirical studies, the more a student will trust this instructor in statistics, the more the student will commit errors. So, and then we measure it as following. We take the number of correct answers by student and his trust. About his trust, we ask directly. The difficulty of this design is following. We need to take the level of understanding of p-value concept by the professor and compare it with the data of his student to really know this connection, if this professor was a real source of p-value test teaching. So, and I propose a questionnaire. It's very simple. We ask status, we ask about discipline, we ask about statistical background, if they participated in statistical courses or not, how long. Then we ask about the source, where they get this information about p-value test, and if they know alternatives, and how do they know if they took lessons about this test at the university, how think their professor is competent. So we ask it directly as to use it as indicator for our hypothesis. So then we just ask the classical questions about knowing the significance test. And same we do for confidence intervals, just to make sure that they're aware that the alternative exists. And here we also ask about, do you have knowledge? Where did you get this knowledge? And do you, how competent you think your instructor is? And a classical confidence interval vignette. And basically that's all. So there are some of my reference, and thank you very much.
Okay, let's say thanks to Olga, first of all. Great talk. And now we have questions for, sorry, we have time for questions. Okay, is there anyone who wants to make a question? People? Okay, I'm here with Thomas. Maybe Thomas.
Hey, Thomas.
Or some kind of commentary.
First,
how are you doing?
Question. Good, good. I just want to thank you first, Olga, for coming. Olga is a colleague, a student, brilliant student that I'm working with for already like half a year. And yeah, it's great to have you because this expands a little bit the scope of researchers that participate in our seminars, which are mainly constrained to Latin America. And now with you, we are opening so to Europe a little bit. I want to ask you, or maybe comment on an issue that, because this fallacy exists, we do a little bit of research on fallacies with Olga actually. So how pervasive do you think is this problem, so that can we give the responsibility to professors to teach this better, or to develop better critical thinking skills, so students will come up themselves with this understanding? So how can you see the way out to this problem? Or do we need to pass a centralized law to change the curricula? Or is it that last alternative? Or is it just a cognitive bias that we cannot escape from?
Yeah, thank you very much. Thank you very much for your question and for your words. This is an amazing question, because this is exactly what we need to, like to decide with all of this problem. And my personal answer would be, first of all, to entirely cancel teaching of this test at the academia, just because of the amount of biases, cognitive, mathematical, calculation biases. And second, promote, or I would say propagate, their alternative tests, like confidence interval, machine learning, and so on. Together, together with critical thinking, of course, to say that you can just take two formulas and based on two simple formulas to examine the whole effect of your research. It's impossible. You need to keep in mind this, and this, and this. And based on this, make a conclusion based on your data. And this is exactly what critical thinking tells us, right? So, and this test also a source of many cognitive biases, I would say. This is what I mentioned before. So you take the probability and you say, aha, this is probability for the hypothesis is true, but it's mathematically wrong. But this is the easy way to make a conclusion. And this is what you always take and put on paper. So there is a big place of this for cognitive fallacies. The role of cognitive fallacies play here enormous role, sorry, for tautology. So I think this problem can be solved from both sides. First, established that people make cognitive mistakes, and this is how to avoid this. Second, make something on publication level, and sorry, for at academical level, some limits, or like, for example, like American Psychological Academia did. They said we won't take any studies which use this method only. So, and the more actions like this should be taken at the academia right now. So yeah.
Okay, is there another person who wants to make a question?
Yes.
Sorry for the noise. There is some people working outside.
No, we don't see anything.
Who is doing a question? Okay, I just have no. Okay, I just want to make commentary first. Okay, this is for students. The article of Olga is published in the Journal of Mathematical Modeling of Biological Systems, which is our journal, the journal of our department here at UTEM. And a short question is more like a curiosity I have about your work. When people study this problem, I mean the NHST problem with I mean, you have your assumptions, but people can study this problem with other assumptions, that people can consider other assumptions at the beginning of the problem or not?
No, with assumptions, what exactly do you mean?
The assumption you show in your presentation, you have some assumptions.
Yeah, you see, yeah, they are the,
yeah,
they
people
are
can have another assumptions.
No, the assumptions I made, it's mathematical assumptions. So if you mean that the null hypothesis is true, that you need a number more than 100, this is a mathematical assumptions which goes together actually with these tests. So you can even start the procedure of this test without these assumptions. The assumption that null hypothesis is true is theoretical. It's given, right? So it's something that's given. But this is exactly the root of the problem, because yes, we say given, yes, we do the whole procedure, yes, we calculate everything, and we make a conclusion in our papers, forgetting to add that actually this conclusion is given, that there is no zero, that there is zero effect. So yeah.
Okay. Thank you, Olga. Is there another person who wants to make a question? Okay, the last question, no? Okay, so let's thanks again, Olga. Thank you so much for your presentation. And
thank you very much.
I'm sorry.
Yes.
Can I ask a question?
Of course you can.
Hello, my name is Rebecca. I'm from the Freie Universität Berlin. I learned the research of Olga, and I'm very curious about the question which can go deeply after the science to like philosophical way. So could you please, Olga, tell me, based on your research, can we continue with this test? Make a research of human experience in families, in schools, on work, to believe in another people, based on how we think, more experience, more knowledges, and such kind of things. Can we go next with your research to more basic things, and how we can make it? What do you think?
You mean that if we can apply this test to the human behavior?
Yes.
This is a very good question. This was my actually motivation for this, because answer is no. And answer is no is because this test is purely mathematical. And it went wrong exactly at the moment when scientists started applying this test to human behavior, which is unpredictable and which may have many other indicators which we don't see. And that's why when we use this test to have some conclusion about human behavior, we say, yes, we can say that we prove the hypothesis, but they always forget to add based on the data and based on indicators we have, because there can be plenty of behavioral indicators, plenty of other variables which we didn't take into account, and that's why we can generalize these results on the whole population, on the whole group, because of the chaotic nature of human behavior. So no, it can be used in our families. It can be used in our not in our families, but also my advice: not use it with your family members. It can be used to explaining the behavior of human only. It should be used in connection with other methods, in connection with some more valid, some more stable methods. Did I answer your question?
Yeah, thank you so much.
Thank you.
Okay. Is there anyone with other questions? If not, let's thanks Olga again. Thank you so much, Olga.
Thank you very much. Gracias. Ciao, ciao.
Okay, people, we are finished our session today. We invite you for the next session. I don't know in which date it will be, but maybe we are going to make the publicity of that event in the next weeks or days. Okay, bye.
Ciao.
Bye-bye.
Olga.